Okay, so today we are going to continue talking about convergence behaviors of random sequence of random variables. Okay. So last time we introduced the first type of convergence called almost sure convergence, and this is among all the convergence types, this is the strongest, one of the strongest convergence. So let's review this one first. So we have a sequence of random variables that each random variable maps outcomes to real numbers. And we say that this sequence of random variables converges to a certain random variable x, the target random variable x, almost surely. This is a notation, almost surely. We say that it converges to x almost surely if the following holds. So we look at this event. This is the event that corresponds to the set of outcomes omega, such that under these outcomes, the realizations of this sequence of random variables converges to x omega. Right? So this is an event. It's a set of outcomes. So we call this an event. Right? It's the set of outcomes omega. Well, these realizations of the sequence of random variables converges to the realization of x. And in particular, this is a sequence of numbers. This is a sequence of numbers converges to this number. So we know in calculus, we know how to determine the convergence of sequence of numbers. If this sequence of numbers converges to x omega under this omega, then we will put this omega into this set. Okay, so this is a collection of all these outcomes where this happens. And almost sure convergence says that this event has probability 1, so it happens almost surely. Now, put it another way, equivalently, we can say that xn omega converges to x omega. Right? This sequence of numbers converges to this sequence of realizations of these random variables converges to the realization of random variable x for almost surely every omega. For almost surely every omega. This almost surely is corresponding to the statement that the original definition where the probability measure of this event equals to 1. Right? In the previous lectures, we call such an event almost sure event. So basically, it says that this convergence happens for almost surely every omega. Yeah. Or you can say that for a set of omega that has probability measure 1. Right. This for a set of omega that has probability measure 1, this is corresponding to this statement. This is the set of omega that has probability measure 1. Well, in this set of omega, we have this convergence. So basically, almost sure convergence requires that the realizations of this sequence of random variables converges to the realization of the target random variable x for almost surely for almost surely every outcome. And we have this simple example to illustrate this almost sure convergence, right? This is a sequence of random variables defined by omega to the power of m. And here we assume the outcome space omega is supported on this interval 0 and 1. And apparently x1 omega equals to omega, so this is a straight line. And x2 omega is omega square, which is a quadratic curve. And if you raise the power continuously, this curve is going to get blended. And in the end, it converges to 0. And we can check that this convergence is an almost sure convergence. Now, if you want to verify the almost sure convergence, essentially you just need to evaluate. You need to identify this set. You figure out the set of all omega where this convergence happens, and then see if this set has probability measure 1, right? So in this example, we figure out that for all this set of omegas, the realizations of random variables, of this sequence of random variables, indeed converges to the realization of the target random variable. And then we look at the probability measure of this set. It is indeed 1. So we claim that this is indeed almost sure convergence. Okay, so this is almost sure convergence. Now, the second type of convergence that we are going to talk about is convergence in probability. This is a little bit weaker. We will talk about the relation among these different convergence types later. So it's called convergence in probability. And and here's the notation to denote this. We say that a sequence of random variables xn converges in probability to a target random variable x. So we write it in this way: xn goes to x and in probability. So there's a p on top of this arrow. And precisely this is defined, defined following this criterion. Okay. So let's look at this one. Now, in this criterion, I'm gonna fix any epsilon first. Okay, you fix an arbitrary epsilon. In fact, you can say you fix arbitrary small epsilon, because epsilon is always going to be set to be very small. Fix any arbitrary epsilon, and we look at this event. We look at this event. We look at the set of outcomes where the realization of xn, the nth random variable, deviates from the realization of the random variable x, and the deviation is bigger than or equal to epsilon. So let's look at this event. We already fix epsilon, right? And we look at this event. We call this EN. This event is the collection of all the outcomes where the realization of the nth random variable deviates the realization of the target random variable. Bigger than or equal to epsilon. Okay, and you can see that once you fix an epsilon, and once we specify the index a a certain random variable in the sequence xn, we can just go over all the outcomes and collect those outcomes that satisfies this criteria, right? So the deviation is bigger than epsilon. And this is a collection of these outcomes, omega, such that this deviation is bigger than epsilon. Now we can call this event En. And then this is an event, so we can evaluate this probability measure. So this probability of this event will give us a certain number. It's a probability number, right? So convergence improbability is achieved when such a probability converges to 0. Okay. So the probability of this event, En, as n goes to infinity, it converges to 0. And this happens for any arbitrary fixed epsilon. Right. So this is the convergence improbability definition of convergence improbability. Right. So in order to verify this type of convergence, what you need to do is to fix arbitrary epsilon. You assume you can fix an arbitrary epsilon, and then you evaluate these events. You find out the collection of omegas where this happens. Right? And this will depend on, of course, on the epsilon that you specified, and also on this xn, specific xn. And once you figure out this event, so in fact, this En, it also depends on epsilon, right? So let's be more specific. Once you figure out this event, you evaluate this probability, right? The probability of this event will be a number that depending on n and epsilon. And then you push this n to infinity. Now, when you push this n to infinity, if this probability, which is a number, right? If this number goes to 0, then you say it converges in probability. So intuitively, this convergence in probability says that, okay, so the set of outcomes, well, the random variable xn deviates from x by an amount of epsilon should have probability measure 0 in the limit. So as n goes to infinity, the deviation of this random variable from x, for most of the outcomes, it should not deviate. It should not deviate bigger than epsilon in the limit. And we can check this simple example that illustrates this convergence in probability idea. Now we have this sequence of random variables. Again, each random variable is defined on the omega space is between 0 and 1. And we specify these random variables, these functions as follows. X1 is a constant function on this omega space. So it's constant 1. And then starting from x2, it is only supported on a half of the omega space. So it's 1 within this half interval and 0 otherwise. X3 is a shifted version of x2 to the right-hand side. Right? So it is 0 in the first half and 1 in the second half. And then x4, we go back to the to this one again, but now it is supported on a quarter of this unit interval. So it's only one within this small interval, 1/4, up to 1/4. Right? X5 is to shift X4 to the right. And then X6 is to further shift X5 to the right. And X7 is a further shift to the right until we reach this the ending point 1. Okay. And you can imagine X8. For X8, we go back again, but now it is only supported on the interval between 0 and 1/8. Right? And X9 is a shifted version of X8. So the pattern looks like this. Okay, and we can see that this sequence of random variables, it has this shifted pattern, and at the same time, the supporting set is shrinking. Okay. At the beginning, we have a support over the entire omega interval, a 0 and 1, 0, 1 interval, and then the support set reduces by half, and then it further reduces by half, and we keep reducing this length of support set by half. And intuitively, you can imagine that this xn sequence is going to getting closer and closer to 0, because you see at the beginning, everything is 1. And then here, only a quarter of the omegas takes value 1. For the rest of the omegas, it takes value 0. And as we keep shrinking this support set, this function is going to be, most of the omegas will have realization 0, right? So it is intuitively, you can imagine it is converging to the 0 function. So this is our target function. Well, it is basically a 0. This random variable has 0 realization for all the omegas, for all the outcomes. Now the question is, for this sequence of random variables and for this target random variable, does this sequence of random variables converge to this target random variable? Now, if so, in what sense? Is it converging almost surely or converging in probability? Right? This is what we're going to figure out by following the definitions. Now let's first look at convergence in probability, the one that we just introduced. We want to check whether or not xn converges to x in probability. Right? And to check that, according to the definition, I just need to check if this one equals to 0. It's the probability of such an event, and this event depends on the epsilon and n. Now, when you fix this epsilon and push n to the limit, the probability of this event goes to 0. So what we are going to do is to, first of all, I'm going to look at this, the probability of this event, which is this one. Forget about the limit first. I'm going to look at the probability of this event. So I'm looking at the probability of this event where xn minus x is bigger than epsilon. And this is a simplified notation, right? It precisely it means the set of outcomes where xn omega minus x omega bigger than epsilon, right? To be precise. Now, this epsilon is fixed and arbitrary, so we don't need to care about this one first. let's look at these two random variables. So we are looking at x and xn. We want to figure out all these omegas such that their deviation is bigger than epsilon. Now, in this example, x, the target random variable, is simply 0 for all the omegas. Right? So this guy is simply 0. So this equals to this one, right? Because the target random variable is simply 0. So we can ignore it. So we just need to evaluate this set. Okay. The set of omegas such that the realization of the nth random variable is bigger than epsilon. Okay. Now this has to do with the nth random variable. So we have to go back and check this sequence. Of course, depending on the index, different xn's will have different support sets, just as we illustrated in these pictures. But if you look at these random variables carefully, you realize that the only difference of these random variables is that their support set is different, right? But the realizations, they either take 1 as the realization or take 0 as the realization, right? These two binary realizations are supported on different intervals. Right? So basically this is a binary these are all binary random variables, but they are supported on different outcomes. So in order for this, according to this criterion, in order for this realization, the absolute value of the realization is bigger than epsilon, right? Because inside we just see that it is binary. It is either 1 or 0. Okay. So if this is 0, if the realization is 0, 0 is never going to be bigger than epsilon, right? So epsilon is any number that is bigger than 0. Okay. So equivalent speaking, we just need to figure out all those omegas where xn omega equals to 1. Because again, all these random variables either take 1 or 0 as the realizations, right? If it's 0, then it does not satisfy this criterion. So for those omegas, it's not gonna be included in this set. So the only other option is when such a realization takes value 1, and 1 is bigger than epsilon, because epsilon is always, we can always assume epsilon is arbitrarily small, a very, very small numerical number. So this event reduces to the set of outcomes where the nth random variable takes value 1. Which is basically the support set of the nth random variable, right? For x3, it is basically this interval. For x7, it is this interval, small interval, right? And then we can see that this support set is shrinking, right? We just mentioned that this is following this pattern, such a support set is shrinking as n goes to infinity. So this one is converging to the empty set, right, as n goes to infinity. So we can claim that the limit, as we push n to infinity, the limit of this is going to be 0. So as we push into infinity, the probability measure of the support set of the nth random variable, right, is going to be 0 because the support set is shrinking by half periodically. Yeah. So this we just verified, right? We start from here. We just verified that yes, in the limit, this one indeed equals to 0. Right? We start from here. And this event turns out to be this one, this probability. And in the limit, this probability indeed converges to 0. So we conclude that this sequence of random variables converges to X, converges to this random variable in probability, right, according to the definition. Okay, so this is the improbability convergence. Now, what about the other one that we introduced before, the almost sure convergence? Does this one converge almost surely to X? Okay, question mark. Well, again, we have to follow the definition, right? To check almost sure convergence, we need to identify this set. If you go back to the almost sure convergence right here, we need to identify this set. Right, so we need to identify the set of outcomes where this sequence of numbers, these realizations of the sequence of random variables converges to the realization of X omega. Okay, and now let's go back to this example and see if we can find out certain omega that satisfy this convergence criteria. And the claim is that for any arbitrary omega, this does not converge. For any arbitrary omega in the outcome, we can show that this sequence does not converge to X omega. Now, let's think about why is the case here. Well, apparently, for any omega, X omega is 0 because the target random variable is 0. Okay. So we just need to look at this sequence of realizations. Now, intuitively, if you look at this, following this pattern, right, you pick an arbitrary omega. Let's say you pick a random point between 0 and 1 here. Now, you start from 1, x1 omega, and this omega is 1. And x2 omega, well, it could be 1 also if this if the point that you pick is between 0 and 1/2. And x3 omega is 0. Okay, so it's 1, 1, 0. And then depending on the specific location that you pick, x4, x5, so it's essentially a binary sequence. But the intuition is that this binary sequence will never stably converge to 0, because at some point, now when we shrink this support set as n goes to infinity, right? So most of the omegas will have realization 0. So basically, you will observe more and more zeros. But on the other hand, since this support set is periodically shifted over the entire interval. So sooner or later, you will always see a certain random variable where the support set covers the omega that you picked. And in that case, the realization will always give you a 1. Okay. So intuitively, this xn omega sequence, no matter what omega you pick, when n becomes very big, you will see a lot of zeros because most of the omegas will have a realization 0 because the support set is shrinking. Okay, in the end, the support set is very, very small. But on the other hand, if you look at this period, although the support set is small, but within this period, these 4 random variables, the support set will cover the entire omega. So one of them will generate a 1 for your choice of omega. So you will always see a 1 somewhere in the sequence, right? Although as n goes to infinity, the 1 gets more and more sparse, but you always will see a 1 that appears somewhere in the sequence. And that violates our definition of convergence of numbers. So you will always see a 1. In order to get convergence, according to the definition of convergence of sequences, right? After some point, you can only see zeros for a binary sequence. But in this case, you will always see a 1 in the end. So the claim is that for any omega, this sequence, which is binary, right, will never converge to 0. Therefore, this set is empty set. We cannot find any omega that such that this convergence happens. So the conclusion is that this sequence does not converge to X almost surely. In fact, because this set is empty set, right, it's kind of it's almost surely this random variables does not converge to X because this is empty. So this is an example where we have convergence in probability, but not almost sure. But later on, I think we will have a conclusion that almost sure will imply convergence in probability, but not the other way. Right? So this is a stronger convergence, but this is a weaker convergence. So this is an example to show that the weaker convergence happens, but not the stronger convergence. Convergence in probability happens, but not convergence almost surely. So these examples tell us that different kinds of convergence, they may have different natures. One may or may not imply the other. So this is everything about convergence in probability. Okay, you've just followed the definition and check this limit. And the third type of convergence is called the mean squared convergence. And it is defined as follows. So we say xn goes to x in the mean square convergence. Xn converges to x in the mean square way if this happens, if this limit goes to 0, equals to 0. Again, you can see that in all these types of definitions, convergence probability, convergence in almost surely, we always have something depending on the limit. But you have to think about you must understand how are these limits applied. What are these limits applied to? Right? In the convergence, almost sure convergence, the limit is a criterion that is included in the definition of this set. But in the convergence improbability, the limit is applied to the probability measure of this event. So my suggestion is that you always follow the definition and to verify these criteria. So let's check this mean squared convergence. So the definition is that I look at xn minus x raised to the power of 2. You can view this as a function of random variables, right? It's a function of these two random variables. You take the expected value of this random variable. Of course, if I know the joint distribution between xn and x, I can do this. I can evaluate this expectation. So this is a number. Suppose we can evaluate this expectation. Right? So this is a number depending on n, depending on which random variable that we are looking at. And the definition says that if this expectation goes to 0 as n goes to infinity, then we claim mean squared convergence. Okay, so to evaluate verify this definition, you just need to evaluate this mean first, and then push it to the limit to see if it converges to 0. And here's an example. xn omega, this random variable is defined as the following function. Between 0 and 1 over n, it is takes values n, otherwise takes values 0. So x1 omega, so the support set is between 0 and 1, and the value, the realization is 1, right? So this is x1 omega. x2 omega, the support set shrinks to 0 and 1/2, but the realization is increases to 2. Right? x3 omega is between 0 and 1/3, and the realization is 3. Okay, so this is the behavior. I should note that this is not a PDF, right? Just to clarify, this is not a PDF of this random variables. This is the illustration of these functions. The PDF will tell us how likely these realizations will occur for different outcomes. But here we are just looking at these functions, not the likelihoods. And intuitively, you can see that as n goes to infinity, this random variables, these squares, is shrinking and also getting taller and taller. So imaginally, this will convert to the 0 random variable because the support set is reducing. Okay, and the question is again, does this one converge to x in the mean squared sense? Well, to do that, we just follow this definition, right? Evaluate this mean and then see what happens in the limit. So write down this mean. Because x is a 0 random variable, so we don't care about x. We can ignore that, it's 0. So we are only looking at expectation of xn squared. And here, the expectation of xn squared, we can calculate that. So xn this is a realization of xn, so it's n squared times the, so I think here we assume, yeah, there's another assumption that says, yeah, the PDF is uniform. I think there must be such an assumption. So all these random variables are uniformly distributed. Yeah, so all these realizations, they are uniformly distributed. Yeah, so that's why the PDF is 1/n. And it's just uniformly distributed over the support set of omega. Okay. So so such a mean, right? So it's the expectation of this xn to the power of 2. So it's n squared, which is the realization to the power of 2 times the corresponding density, 1/n. So this 1/n is not the, it's actually the integration between 0 and 1/n. So you get this integration over 0 and 1/n gives you 1/n. So this is the mean. And then these two gets canceled, you get an n out of the this expectation. So clearly this is not going to converge to 0. Well, we need this goes to 0, and this is diverges to infinity. So it does not converge in the mean square sense. And then we can, for this example, we can check the other two criterions, almost sure and the improbability. So let's again look at almost sure. For almost sure convergence, we need to identify the set of omegas where this convergence happens. And here the claim is that for any omega between 0 and 1, excluding 0, and this sequence is going to converge to 0. Because you can see that the support set is shrinking to the left. So for any arbitrary omega that you pick between 0 and 1, excluding 0, for example, if you pick it here, then at some point, xn, the support set of xn will be to the left of this point. And after that, all the values of xn will become 0, right? Because the support set is shrinking and shrinking. So it goes to, in the end, it stays on the very close to the horizontal, this vertical curve, the y-axis. So for any such omega, the sequence will, in the end, will converge to 0. Now, except for 0, now what happens at 0? At 0, you see that x1 equals to 1, x2 equals to 2, x3 equals to 3. So at 0, this sequence diverges to infinity, 1, 2, 3, 4, up to infinity, right? So this point, 0 is not included in this set. At 0, we don't have convergence. But that doesn't matter because this interval already have probability measure 1. Okay? Because at 0, the probability mass is 0. This is a continuous case. So in this case, we have almost sure convergence. We have almost sure convergence. Now, what about improbability? Well, later on, we can always say once we have almost sure convergence, we are guaranteed to have improbability. Okay, but here we can just follow the definition and verify this. So for improbability convergence, we look at this this event, the probability of this event. Well, X in this example is the target random variable is 0, so we can ignore that. So this reduces to this event. Xn bigger than epsilon. And we can see that for arbitrary small epsilon, right? If you draw a vertical, if you draw a horizontal line at epsilon, right? You can see that Xn, the absolute value of Xn will be bigger than epsilon on their support set, right? Because for all these random variables, they are either take values of n or 0, right? So in order to be bigger than epsilon, that clearly this n will be bigger than epsilon if your epsilon is very, very small. And this n is supported on this support set. So basically, this event is your support set for the nth random variable. And the support set is between 0 and 1 over n. And this has a probability measure 1 over n. Yeah. Again, here, I think we assume all these outcomes this interval has probability measure 1 over n. And it converges to 0. Converges to 0 as n goes to infinity. So indeed, it is a convergence in probability. Okay, so this is the mean square convergence. You follow this definition, you evaluate this mean for the nth random variable and push it to the limit. Now the last one is called convergence in distribution. It's a very weak type of convergence. So we call xn goes to x in distribution. Now this is notation D, in distribution, if the following holds. And this it looks very simple. We simply require that I look at the CDF function associated with my target random variable x. So it's capital F, capital X, and I evaluate the CDF function at x. And if this one equals to the limit of the CDF functions of your sequence of random variables, well, this equality holds at all continuous points of the CDF function. Then we say we have in distribution convergence. Okay, let's look at this one again. So it says that, so I look at, I have the CDF function of my target random variable, and I have the CDF functions of my sequence of random variables, right? So this is a sequence of CDF functions. This is a target CDF function. Now for every small x, I can check for every small x, this CDF function will return a number between 0 and 1 because it's CDF function. And this is a sequence of numbers between 0 and 1. Okay. I want to check if this one in the limit equals to that one for a specific x. If this limit holds, if this convergence holds for all continuous points of fx. So for all the points x, well, this CDF function is continuous. Okay, then we say that xn converges to x in distribution. Now put it other way, we simply say that fxn, this sequence of numbers converges to this one for all continuous points. So except for those discontinuous points of the CDF function, right, we always have this pointwise convergence. Fix any x, well, this is continuous. This is always going to converge to fx. So it's called convergence in distribution. Now, this is a very weak type of convergence. And the following example will give us an idea why this is very weak. So consider the following sequence of random variables. Again, it is supported on 0 and 1. So x1 looks like this. It is 1 in the first half interval, 1/2 in the following a quarter of the interval, okay? And 2/3 in the next quarter. And x2 is simply switching the first two intervals. So it is 1/2 in the first quarter, and then 1 in the follow-up half interval. Okay. And x3, I think it is it looks like it is 2/3 in the first quarter, 1/2 in this following up quarter. Right? So basically, these three random variables, they have the same set of realizations, either 1, 2/3, or 1/2. But these realizations are supported on different intervals. Okay, that's the basic idea. So this is x1, x2, x3, and this is periodic. So x4 will equal to x1, x5 will equal to x2, x6 will equal to x3. Right? So this is such a periodic sequence of random variables. Now, what happens is that you can check that all these random variables have the same CDF, and the CDF function looks like this. Now, for example, let's look at the first random variable, x1. And this picture shows the CDF function of x1. Why is that case? Well, if you look at this random variable, we have that the probability, because we only have 3 discrete realizations, right? So the probability mass function, we can describe this random variable by the probability mass function. I look at the case where x1 equals to 1, 2/3, and 1/2 respectively. These are the only 3 discrete discrete realizations of the random variable. Now, the probability that x1 equals to 1 is 1/2. Why? Because it is supported on the first half interval. Yeah. So this is the event, right? This is the event that collects all the outcomes. All the outcomes where x1 takes values 1. And the probability measure, so this event is essentially the interval between 0 and 1/2. It has a probability measure 1/2. Right? And similarly, for the second case, 2/3, it is supported on this quarter interval. So the probability is 1/4. And similarly, for this realization, 1/2, it is supported on this interval, also has probability measure 1/4, right? So this is the PMF of this random variable. And you can check that for X2, X3, their PMF is the same. Although the realizations are supported on different intervals of outcomes, but the probability measures are the same. So they have the same probability mass function. They have the same distribution. And therefore, because the PMF is the same, so they all have the same CDF, a cumulative distribution. Okay. And CDF takes this stepwise, is a stepwise function, because this is a discrete random variable. Okay. So we conclude that the CDF of X1, X2, X3, they are the same. And because the sequence of random variables is periodic, so the conclusion is that all the CDF functions, all the fxn, they are the same. Right? They equals to fx1. They equals to fx1. Right? And because they are the same, so we can conclude that, well, you take the limit. You fix any, you evaluate the CDF function at any continuous point x, take the limit. Of course, there will be, this limit will equals to that one, because the functions, the CDF functions themselves are the same. So this concludes that this sequence of random variables converges in distribution to x1. In fact, to any of them, to x1, to x2, to x3. Right, so it satisfies the convergence in distribution criteria. However, why this is called a very weak type of convergence? Because you can clearly see that these random variables, they look very different, right? They look very different. The functions look very different, but somehow their a CDF function has the same behavior. So this although this xn converges in any of these random variables in distribution, but you can see that it could happen that these random variables looks drastically different. Well, for all the previous convergence types, right? When we say, okay, this sequence of random variable converges to X, this zero random variable, right? In distribution, in probability, almost surely, or in mean square sense, we all get a intuition that the shape of this function will eventually get very close to the target random variable. But in this case, for example, the sequence of random variables, the claim is that the sequence of random variables converges in distribution to any of them. Well, to x1, for example, but x3 looks very different to x1. And the sequence is periodic, so you will have endlessly many random variables that has this shape that is very different, looks very different to x1. But in the end, it satisfies the definition of convergence in distribution. Okay, so this is a very weak type of convergence. It only requires the CDF function to have a certain convergence behavior. But the CDF function is a cumulative information of the random variable. So it does not necessarily imply a very strong convergence behavior on the random variables. In fact, I think you can check that for this example, we do not have any other type of convergence. This sequence does not converge in probability almost surely or in the mean square sense. right? So this is the weakest type of convergence. And this is the relation between all these four types of convergence of random variables. I will skip the proof here, but essentially almost sure and mean squared, they are the strongest. They do not imply each other, but both of them can imply improbability convergence, and the improbability can imply convergence in distribution. Right? So these are different, the relation between different type of convergence. And we can see that this is the weakest, because the random variables themselves can look very different. But all these, they can guarantee at least the random variables, eventually they will more or less look the same. And we have the following example. Yeah, I think we can go over this example. This is a random process, and that satisfies only part of these convergence behaviors. Okay, so let's look at it. It's a random, it looks like a random walk. So we have a sequence W0, W1 is a sequence of IID Gaussian random variable. Each one is a random number generated according to the standard Gaussian distribution. Right? IID, identically and independently distributed. So they are identical, means all of them follow this Gaussian distribution. Independent means they are independent. Okay, it's very clear. Okay, so basically you use MATLAB to generate this, a bunch of Gaussian random numbers. Now what you do is that you start from 0. This is the initial point on the, let's say on the x-axis, on your axis. Start from 0 and you do this random walk. What does this random walk do? The next step is the previous step times 0.9 plus this noise. That's 0.9 times your previous location plus the next noise that you generated. And this will create a sequence of random variables, xn, right? And we will check the convergence behavior of xn. We'll check the convergence behavior. So the claim one is that it does not converge in probability. Well, we can check the convergence in probability criterion in order to. So to check convergence in probability, we need to look at this kind of events: xm minus x greater than epsilon, and push it to the limit. So I think here I will, okay, let me point out the logic. So we are going to show this one. We are going to show this one. We are going to show that this xn, for any random variable x, this xn will deviate. Xn minus x, the deviation is bigger than 1. So this 1 could be this epsilon. Right? We can find an epsilon which is 1 such that this guy for any x does not converge to 0. So it violates the definition of the improbability, convergence improbability. But how do we prove this claim? Now this claim is very strong because this does not converge for any x. We need to show this does not converge for any x. How do we reach this conclusion? Let's follow this logic. These are the intermediate steps. Because Wn is Gaussian, standard Gaussian, so we can check these two, right? This is simply the CDF, following the CDF, the phi function of standard Gaussian. Numerically, we can check this is bigger than 2%. Now we look at this event where xm minus xm minus 1. So this is like the increment between your two adjacent steps. The increment is bigger than 2. And we can show that, well, this requires a little bit thinking. So we can show that this event is a bigger event than the union of these two. Why? I think that so first of all, these two are disjoint events. I think both of them can imply this one. Right, for example, if this is let me check this one. Xm minus xm minus 1 equals to, according to this random work, it equals to 0.1 xm minus 1 plus Wn. Right, so this is essentially this one. This absolute value. You can add the absolute value. Now, if this is bigger than 0, well, this is smaller than -2. So I'm not sure. Why open 1? Well, this is open 9, right? So xn minus xn minus, so xn equals this one. Oh, I see. Yeah, this one minus xn minus 1. So we should have, we should have negative. Yeah, there's a negative sign here. Negative open 1 xn. Right? Because xn equals to 0.9 xn minus 1 plus this one. And then you subtract xn minus 1. So 0.9 minus 1, you get negative 0.1 xn. Okay. So it's Wn minus 0.1 xn minus 1, sorry. Okay. So according to the definition of the random walk, the increment is equals to this one. Okay, now let's check that both of these two, I think, subset of, so these two events is a subset of this one, because in the first case, this is bigger than 0, so this is a negative number, and this is less than -2. So this is less than -2, while this is less than 0. So this is bigger, guaranteed to be bigger than 2 because we take the absolute value, right? And similarly, you can verify that this also has the same implication. If omega Wn is bigger than 2, well, this is smaller than 0. So this will be a positive number. 2 plus a positive number, again, is bigger than 2. Right? So this 2 implies that one. And because xn minus 1 and wn, they are independent. They are independent. Why? Because xn minus 1 is created according to this recursive random walk. Xn minus 1 is created by W0, W1 up to Wn minus 1. Right? So this depending on the previous all noises. But Wn is independent from all of them. Right? So therefore, Wn is independent from Xn minus 1. Now, by independence, we can separate this joint event into the product. And then we can utilize these two, this numerical estimate. Both of these two is bigger than 0.2. So it's greater than or equal to 0.02 times the addition of these two. Okay. And these two are complementary to each other. So it's bigger than, these two are complementary. So it equals to 1, it's probability 1. It's bigger than 0.02. So the conclusion is that the probability that the increment is greater than 2 is bigger than 2%. Okay, you have 2%, you have a more than 2% chance so that the increment is bigger than 2. This is an intermediate result, okay, which means that in this random walk, you have a non-negligible chance to take a large step. Okay? You have at least 2% chance to take a large step. So that's the intermediate important implication of this random walk. Now, based on this observation, we can make our claim. Now, how do we do the following proof? Based on this, we can prove that xn cannot converge in probability to any x. Why? So we looked at let me think about this. Let's look at this two first. You pick any random variable x and look at this deviation, these two probabilities. Probability xn minus x bigger than 1, xn minus 1 minus x bigger than 1. This is like the deviation in the consecutive in two adjacent iterations, right? But you are looking at the case where the deviation is bigger than 1. Okay. Now, based on the union bound, this is bigger. These two addition of these two probabilities is bigger than or equal to the probability of the union event. But based on the probability law, the probability of the union event is less than or equal to the sum of the individual probabilities. Okay, so here's a union bound. Apply the fundamental axioms of probability laws. Okay, why do we want to do this? Because once we have this union bound, and this is a union event, right? Either this deviation in xn bigger than 1, or the deviation of xn minus 1 is bigger than 1. And this union event would imply this one. Okay. So why is that case? Because because xn minus xn minus 1 equals to this one, and less than equal to the sum of these two by the triangle inequality. Okay. Oh, I make the wrong claim. I think this is a smaller event. This one would imply these two. Yeah. Because why? Because if this happens, if this one is bigger than 2, right? This one bigger than 2, so this one is bigger than 2. If this one is bigger than 2, then, and this is guaranteed to hold triangle inequality. So basically, the sum of these two is bigger than 2. So we must have one of them is bigger than 1. Right? The fundamental observation. If the sum of two numbers is bigger than 2, one of them must be bigger than 1. Yeah, so that's why this probability is bigger than equal to this one, because this is a smaller subset, the sub-event of this one. But this is basically to get rid of x, and only consider the increment, relating this to the increment. And we just conclude that this probability is bigger than 0.02. So why is this important? Because once we have this, the conclusion is that the sum of these two is bigger than 0.02. Right. So sum of these two bigger than 0.02, it means that one of them must be bigger than 0.01. And this happens for n in x. The entire proof, right? We did not specify, we do not have any requirement on the target random variable. And we do, and all these bounds holds for arbitrary n. Right? We do not specify the n. There's no requirement on that. So from this one, the conclusion is that the probability of xn minus x bigger than 1 is guaranteed to bigger than 0.01 for n in n and x. And this clearly violates the definition of convergence in probability. Right? Convergence in probability says that you can find an x such that this probability goes to 0. But this claim says that no matter what x you choose, this probability is always bigger than 0.01. Right? So this shows that this random walk does not converge in probability. Right? It violates the in the entire universe, you cannot find any random variables such that it converges in probability. Yeah, I know this the logic is a little bit tricky. It proves a little bit tricky here. Yeah, but this is the nature of random walk, and in this case, it seems much simplified because everything is IID, independent. Okay? So we don't need to worry about the correlation between these noises. Okay, so this is an interesting example about random walk, and we can check that. I have 1 minute, but I want to go over this one. We can check that it converges in distribution to a certain random variable. Okay, why is that? Well, this is our random walk, and let's do this one by one. Starting from x0, the initialization. Okay, x0 equals to, so x -1 is 0, right? So in the first step, this is 0. So x0 equals to your first noise, w0. Right? But we know w0 follows normal distribution. So this is x0. x1 equals to 0.9 x0 plus w1. Okay. Well, this is a linear combination of two Gaussians. Right? X0 is Gaussian, W1 is another independent Gaussian. You can check that, right, using the linear, all those transformations for random variables. You can check that this has follows such a Gaussian distribution. Okay. We know linear combination of Gaussians is Gaussian, right? So you just need to work out the mean and the variance of these two guys. And then you keep going, x2 equals to 0.9 times x1 plus w2. But w1 follows this Gaussian, x1 follows such a Gaussian distribution. W2 follows a normal distribution. But again, you do another calculation, you can calculate the distribution of x2. And you can check that xn follows such a Gaussian distribution. There's a zero mean, but the variance 0.9 squared times the variance of the previous the variance of xn minus 1 plus 1. But the variance for the variances, you can based on this random walk, you can establish such a relation between their variances. The variance of xn is 0.9 squared of the variance of xn minus 1 plus 1, because the variance of this one is 1. And with this recursion, you can work out, right? You can work out these variances. But in the end, you can see that the previous variant, the next variance is the previous variance times 0.81 plus 1. And this is going to be you can check that such a recursion will converge to a limit. Okay. The limit is to basically set these two to be equal. Okay, you assume there's a limit, set them to be equal, and you can solve that. The limit is about 1 over 0.19. So in the end, you can say that xn in the end, the sigma xn, the variance of xn is goes to this value. Okay. So it converges in distribution to such a normal distribution. Right. So in the end, this random walk, right, only obeys a very weak type of convergence. It does not converge in probability, but converges in distribution. So meaning that in the end, if you look at the sequence of random variables, because the random walk can go to anywhere in the space on the axis. So in the end, the xn may look very different, right? Just like this example. They may look very different, but they follow the same distribution. They follow the same CDF function. Yeah. And this is why these type of convergence are very important whenever we need to deal with random walks or random process. So the last part, this part is to say that all the previous criteria, these 4 types of convergence, right, almost sure improbability mean square, we can, because all these type of convergence involves a limit, right? It involves a certain kind of a limit. And this is to say that when we talk about limit of numbers, we have 2 different ways. One is the epsilon delta language. The other is this Cauchy criterion. So it is an equivalent way to define the convergence of real numbers. And the idea is that, okay, since this is an equivalent way of definition, we can replace all the limits in these definitions by this Cauchy criteria. But I think we probably don't need this. Yeah, if you are familiar with the Cauchy criteria in calculus, you can. Sometimes these criterions will be more convenient. Yeah, but I think we probably don't need this in the homeworks, so I will skip that. Okay, so okay, I think I will stop here, and yeah, the next topic will be the limit of sum of random variables. So that will be relating to this law of large numbers. But I think when you go back home, you can go over all these four types of convergence and see if you can tell their differences. It's a little bit tricky, but always when you want to verify them, always follow the definitions. Okay, as we have done in today's lecture. Okay, so I will stop here, and I will see you in the office hours at 1 p.m.